Okay, so this is conservation of mechanical energy today, and we're bringing back the ramp, and we're bringing back my sedan at the top of the ramp, and we also need to bring back our cat down here at the bottom. Okay, now our car we're actually going to let drop this time. Okay, and the cat is going to fall. And right now it has an initial position of... We have initial position of Y initial. Okay, and down here, the instant before it touches the cat, because we don't kill cats in here, it's just fun to think about. So, that's going to be our final height down here. Okay, and this is the positive y-axis. All right, the force acting on our car of mass m, by the way, our car has mass m. The force acting on this car is, of course, mg, and the force right down here right here, the moment before it touches the cat, okay, the force acting on this thing is still mg. All right, so the potential energy of this car right here is, and if we take this down here by y final level, this equals, okay, this is y equals 0 at this height. Okay, our potential energy is going to equal mg times our initial height. That is the potential energy that this car can exert on. This is how much work this car could possibly exert upon the cat when it squeezes it between itself and the ground. Which we won't actually do because we don't like to kill cats in here. We just like to think about it. Alright. So, when this happens, and the car drops, gravity, okay, did positive work. All right, well, we know that the net work on something is equal to the change in kinetic energy on that thing. So, work, no, not F, okay, work equals the integral of F dot dr. I'm not going to bother with the vectors yet, okay, which is equal to delta K, but delta K we also know equals, whenever we have a delta, it means what? Okay, it's the change in, which is defined as our final minus our initial. So, K final minus K initial. Whatever kinetic energy we started with, subtracted from the amount of kinetic energy we finish with. Alright, well that gives us integral of y initial to y final of mg negative j hat times dy j hat, okay, which gives us negative mg y from y initial to y final. Okay, which also equals, so negative mg y final minus a negative mg y initial. Follow me there? Okay, and it's probably what I should have done the first time. Okay, when we figured this out yesterday. We factor a negative out of this. Okay, and we get mgy final minus mgy initial, okay, which is negative u final minus u initial. I know I'm getting kind of low here. Which really just equals negative delta u. Okay, this is a huge idea here. Okay, so what really happens here is the work done by gravity the work done by gravity equals our negative change in kinetic energy. Okay, so the work done by gravity equals the negative change in gravitational potential. However, what did we assign our work done by gravity to equal to begin with?
Negative, no.
Okay, it also equals our change in our kinetic energy. This is an important concept. The amount of kinetic energy an object gains when it falls is equal to the amount of potential energy it loses. The amount of kinetic energy you gain when you fall is equal to the amount of potential energy you lose when you fall. That potential energy turns into kinetic energy, just as merely as an effect of the work being done on the object. Okay, so another way of writing this then is delta K plus delta U equals 0. Or your change in your kinetic energy plus the change in your potential energy will always equal 0, assuming we have a conservative force. And we'll talk about this, talk about a conservative force another time. But it's pretty much when work done by gravity, if you have work done by gravity, the total amount of kinetic and potential will not change. Now, you can have positive amounts of kinetic and positive amounts of potential. Okay, both of those values can be huge. But if one of them changes, okay, if one of them increases due to gravity, the other one will decrease. Okay, to the point where you have no net gain of energy. All right. Okay, so if we have something that is not changing, if something's happening to it, but our total amount is not changing, okay, our energy is not changing, our energy is conserved. This is the important, this is, okay, our energy is conserved here. Now, we can write this in another way. Okay, delta K is Kf minus Ki, okay, and delta U, or change in potential, is Uf, yucky, minus Ui, and that's going to equal 0. So, we can rearrange this so that let's just rewrite that, because that was a travesty. Plus U final. Okay, so our total final energy, our total final potential plus our total final kinetic is going to equal our total initial. Okay, and we have a term for this. Okay, so our final conditions, our final kinetic plus our final potential equals our total, our initial potential plus our initial kinetic. Okay. When we take these two terms, K plus U, okay, we have a term for this. Okay, in fact, it is a definition. K plus U is defined as the mechanical energy. Okay, K plus U equals the mechanical energy. I will refer to it sometimes in here as TME, as total mechanical energy. Okay, so our kinetic plus our potential, this only works our kinetic plus potential only works, this whole thing staying constant, only works if under gravitational, force, and under elastic forces. Okay, also known as a spring force. Okay, these are the big two that we'll be dealing with. There are a couple other places where it happens, but these are the two that we're going to deal with in this semester. And so I'll give you what it is for a spring, just for we can derive it some other time, or you guys can figure out how to derive it. It's not that difficult. It's pretty much the same thing. U elastic potential elastic energy. The elastic potential energy stored in a spring is 1/2 k x squared. And if you remember that x is, it's not truly displacement. It's how far off of the equilibrium value of the spring is, whatever your equilibrium value of your position is. That x is the x squared. But you can kind of tell, you know, the 1/2 kx squared kind of looks, there's a familiar feel to it if you think about 1/2 mv squared. So it should make some sense to you, although if you realize that this is potential, this is not kinetic. Yeah? Okay. So this brings us to, you need to change up here a little bit. The conservation, okay, of mechanical energy. Conservation of mechanical energy. That our total mechanical energy that we begin with equals that with which we finish. Delta E equals 0 if and only if. Yes, we've got the double if in there. The only forces doing work are gravity and springs. And that's it.